Thank you.
Okay, thank you for the introduction. First of all, I would like to thanks organizers for this opportunity to give a talk here. Especially, I want to thank the Professor Wilson for every efforts he made for this wonderfully organized conference. Okay, so what I'm going to talking about is that as you see here, minimality of the rational maps with a good reduction on the project line of QP. Here is the outline of my talk. The first part one is a kind of the brief introduction to the goal of talk. And then in part two, actually, I'm going to talk about the two dynamical system on the periodic setting. And then in the final, in the part three, actually, I'm going to talking about the minimal criterion for the convergence series of the GP. Okay, as a main part, finally, I'm going to present minimality criterion for the rational maps with a good reduction on the project line of the QP. Okay. I want to start with by saying that the goal of the talk. In this talk, actually, I'm going to provide the minimality criterion of the rational maps of degree at least 2 with a good reduction on the project line. Due to this criterion, actually, we can obtain a complete description of the minimal these conditions for such a map on the project line in terms of its coefficient, especially for the case p equal to 3. And then on the other hand, for the arbitrary prime p greater than or equal to 5, then we can come up with a method of characterizing the minimality rational maps of degree at least 2 on the project line, provided that the prescribed condition for the reduction of this map on the project line of finite field Fp to be minimal or transitive explicitly known. Okay, as a kind of the prerequisite, we have to characterize the minimality criterion for the convergence series of PAD integer in terms of its coefficient for arbitrary prime p. Okay, right here, actually, I should say that this is going to work with Do-Young Gu and Yongjae Kwon and Young Kwon. Okay, so I'm going to start with the basic thing, the periodic measurable dynamic system on the periodic settings. So you might wonder what are the periodic dynamic systems? You might know this answer for this question. So I'm in the two objects I'm interested in this setting is that first the periodic measurable dynamic system on GP, which is made of the 3 objects GP, F, and mu, where GP is just ring of periodic integers equipped with the periodic absolute value associated the additive periodic valuation VP. Okay, and then from now on, actually, I'm denoted the quotient field of GP by the QP. And then the second object F is just the measurable function on GP. Usually, most of the cases is a continuous function. We are working on the Borel sigma algebra. So the last object is mu is this normalized Haar measure on GP, such that the measure of the entire space is 1, as it was talked by the previous talk by the Professor Sinclair. Okay, now I'm going to remind you that what is the measure of the ball on the periodic integers. Okay, here is the definition. The measure of a ball of the form a plus p to the ng is defined as its radius, namely the p to the minus to the n. Okay. Another dynamic system I'm interested in is that the periodic topological dynamic system on the project line of QP. You see it consists of this project space and the rational map as a transformation on it. So as you see here, the project line of QP is it has the periodic caudal metric, which is defined by this formula. You might be familiar with this formula. this is kind of the periodic analog of the spherical metric on the Riemann sphere. Okay, so one can observe that actually this caudal metric between the two GP points G0 and G0 and G1 is same as the periodic distance in between them. Okay, so let's go to the next slide. Okay, so I'm going to define the one-its function on the two different dynamical systems, as I mentioned here. So here is the definition. F is said to be one-its continuous on GP if the following equation is true. That means that you see the distance between f of x and y is less than or equal to the distance between x and y for all x and y in GP. Okay, and then the map on the project line of QP is said to be the one-its continuous if the same inequality is true for the distance replaced by the caudal metric in the periodic case. I mean the rho of pi of p and pi of q is less than the caudal metric p and q for all p and q in the project line of QP. Okay, so what can observe is that actually whenever you have the one-its function, then it induces the a sequence of the reduced function on the quotient space G P mod P to the n to the G to itself. Okay, so this sequence of function plays a major role in the characterization of the minimality of functions. So let me give you the example of the one-its function on GP. The space of the one-its function contains several subclasses. For example, the polynomial with the integer coefficients, even in the coefficient in GP. Also, it contains the set of the analytic function on GP inside in the GP double bracket X. Actually, this is called we just call them the set of the convergent power series of GP. And also, it contains a class of function of a B class of functions, which was defined by the Anashin, who it was introduced by the Anashin in his talk on the first day of this conference. Okay, this function has a nice property, like it has a nice, Taylor series expansion. Okay. So now I'm going to talk about the reduced function on the one-its function on the project line. So first of all, the project line, it consists of the set of p plus 1 times p to the n disjoint balls of the radius p to the minus n. These balls are defined by this rule. Bn b sub n of x. Okay, now the beta n sub n denotes the set of such balls. So in terms of the graph, actually we notice that for each n there is a one-to-one correspondence between the set of beta n and the set of the vertices of the tree at the level n. Okay, suppose we have the one-its function of the project line, as in the case for the periodic integers. Actually, we have a sequence of the reduced transformation on the beta n to itself, defined by this rule. Okay, so the pi sends the ball of the radius p to the n to the ball of the same size but different center. Okay, and now I'm going to summarize the basic property for the convergent series in the GP double inequality sign. Okay, first of all, every series, convergent series has turns out to be the one-its function on GP, and also this ring is closed under addition, multiplication, and differentiation, and even composition. Okay, thirdly, this function has a nice property like the Taylor expansion at any point. Okay, when you have when you see this, the Taylor expansion, actually the important thing is that its Taylor coefficient is p-adic integers. I mean the nth derivative of f is divisible by the m factorial for all integers m. Okay. So also, I mean the power series, I mean convergence series with the coefficient QP is the complete normal space with respect to sub norm. And then the kind of the extension of the division algorithm for the polynomials in integer coefficient, I mean p-adic division algorithm for this ring works, but I'm not going into details about this one. Also, the p-adic wire stress preparation theorem for the this ring holds. I mean, p-adic wire stress preparation theorem says that it gives you kind of the decomposition of the power series into the polynomial times the unit elements in the ring. Okay, so let me remind some of the typical, I mean, terminology in the p-adic the dynamic system. Okay, so here is the definition for the measure preserving. F is measure preserving on the p-adic integer. Then for any measurable set, its inverse m and its inverse has the same measure. Then we say that f is a measure preserving. And then if f is a measure preserving, then f said to be the ergodic if it has a proper embedded subset, by which I mean that the measure of m is equal to 1 or 0 for any measurable invariant set at set m, I'm sorry, in GP. So we can talk about the same thing, more or less the minimality, kind of the analog of the minimality for the topological dynamic system. So E is invariant, pi invariant subset for the project line of the QP with the transformation pi. Then the subsystem E and pi is said to be the minimal if the orbit of X under this map is dense for all X in E. Okay, so we are interested in the kind of the minimality of the transformation on the whole space. I mean, the project line of QP. Okay, here is I want to talk about the basic factor of the p-adic dynamic system. So proposition 1 says that f, suppose we have the one function on GP, then the following is equivalent. So GP f is a minimal. I mean, the f is a minimal on GP if and only if the its reduced function is minimal on the quotient space GP mod p to the n GP for all positive entities n. Okay, and then which is also known to be the ergodic. Okay, so because from this proposition, actually we know that the minimality and the ergodicity is equivalent each other on GP. In particular, if we have the convergence series, okay, then the dynamic system is minimal if and only if its reduced function is minimal for the smallest level mu for which the f is minimal. I mean, here's the mu is defined as the 3 for the case p equal 2 or 3, mu is 2. Otherwise, for more general case, mu is 2. Okay, because of this the property, we can determine the minimality of the function convergence series for the smallest level for which f is minimal at 3 or 2. Okay, the same thing is true for the continuous function on the project line. Okay, so suppose we have the one function on the project line of QP, then the project line, this pi is minimal on the entire space, project space, if and only if the system in this system is minimal for all integers, positive integers. In particular, if pi has a rational map, I'm sorry, pi is a rational map with a good reduction, then product line is minimal, and if the its reduced function is minimal, where mu is the same in the observer. Okay, so now, now I'm going to talk about efficient minimality criterion for the convergence series, which is this states that we have the convergence series in GP such that its reduced function is minimal at the level n, fixed n. Then the following is equivalent. I mean, the reduced function at the next level n plus 1 is also minimal. Then this is equivalent to the second statement. For all g in GP, we have the f to the p to the n iterate x minus x is divisible by p to the n, but not divisible by p plus n plus 1. Okay, so derivative of f to the p to the n is just 1 unit in GP. Okay, the statement for 2 is true for only 1 point in the statement 3. So in this case, if there is at least 1 point, then such that satisfying these two, the same condition in the statement 2. So usually we take the x to be 0. Okay, so this is the one remark I have to point out is that this is the case where the cycle of the length p to the n that rises from the nth level f to the f sub n grows in the well-known linearization arguments for the minimality. Okay, now so the analog of the rational map with good reduction on the product line also works. Okay, now I'm going to introduce the another minimality criterion for the periodic series convergence series for prime p. As I said before, mu is 3 for the case p equal to 2 or 3. Mu is 2 for general prime p bigger than or equal to 5. And then we take the functions depending on p, which is g choose p square for p equal to 2 or 3. This is a binomial coefficient function. And then delta of g is g choose 2p for the general case. Okay, so this is a integer valued function with the coefficient in qp. And then the theorem says that let f is a convergence series. F is minimal on GP if only if the reduction of f modulo delta x is minimal on the GP. Its remainder is minimal on the GP is equivalent to that the minimality of the given convergence series. Okay, so the proof is really simple. So if when we use the periodic division algorithm for convergence series, then we can write the quotient and its remainder. Okay, when you see that here, you observe that the p to the mu divides the factorial of the degree of delta for all p. So that's why f of x and p its remainder r of z are congruent modulo p to the mu. So we have this result from the proposition 1. Okay, because these the f and its remainder satisfy the minimal, the level for the minimality of the given convergence series. Okay. Okay, now I'm going to lay out kind of the complete minimality criterion for the various functions of GP. P in the case p equal to the first time the Rarin characterize the minimality of the polynomial in the G2 polynomial. So f is minimal if and only if the following relations is satisfied. I mean, we have the full congruence, but which is equivalent to the conditions on the derivative of the f to the 2 iterate, and this is kind of the condition comes from that the f3 is minimal on the level 3. Okay, so Durant and Picot presented another minimal criterion for the polynomials of G2, which turns out to be the equivalent of Larin's criterion. Okay, moreover, Anacin characterized the minimality of the convergence series of GP. In general, actually, he gave the complete minimal criterion for the one-hit function in terms of the Mahler expansion coefficients. Whenever you have the Mahler expansion for f, then he come up with the criterion, minimal criterion, completely in the case of the p equal 2. But more general case, yeah, it is unknown for the minimality in terms of its coefficients. Okay, so in the case p equals 3, then I'm going to give you the complete minimality criterion for the convergence series. Okay, Durant and Picot presented minimality criterion for polynomials of 3D integers on the assumption that f of 0 is 1. Okay, to describe our result, actually, we need to set up the quantities A0 and A1, D0 and D1, and then with for simplicity, D1 prime is the sum of D0 and D1. D2 prime is minus D0 plus D1. Actually, this turns out to be the relate to the values of f at 1 or derivative of f at 1. Okay, so here is the complete description for the minimality for the convergence series. Okay, f is minimal if and only if the f fulfills the one of the 8 conditions. Okay, let me go on there, expand on this. So setting the vector consisting of the A0, capital A1, capital A0, A1, D1 prime, D2 prime, modulo 3. Okay, so one of the minimality condition is that the product of its derivative at 0, 1, and 2, I mean, product of A0, A1, D1 prime, D2 prime is equal to 1 modulo 3. So that's why we have 8 cases, okay, for these vectors. So we have case by case. Actually, we have corresponding conditions for the minimality. Okay, we have 4 more cases. Okay, so when you look over Durant and Picot's criterion, actually there is terms of high powers of the constant term, because they use the kind of the normalization like this form using the constant term A0. But in our result, we don't have any kind of this kind of things. Only the natural, I mean, the expression in terms of the coefficients. Okay, so now let me give you some idea of the case p equals 3 and more general case, because we have to use the lemma A, which says that f is minimal on the 3D integers. It is if and only if the following conditions are satisfied. I mean, this is a condition arising from the minimality of f at the level 3. Okay, so it involves with the derivative of 3 to the f to the 3 and second derivative of f to the 3 at the point equal to 0. So what we can do is that actually we have to use an argument in linear algebra and decompose f into a sum of the polynomial, sum of the this form. F is r of x plus 3 times h of x, where r is just the minimal polynomial of degree less than 5. And also h of x is known to be the some one-Lipschitz function. This is the key for the minimality. Okay, so one remark I want to point out is that the PAD virus stress preparation theorem enables us to adapt this method for this case to the more general case, along with the following lemma, which says that the F is a convergence minimal series if and only if the following conditions are satisfied. The first, F is transitive modulo P. In other words, F is minima at the level 1. And then the derivative of F to the P at 1 is 1 unit modulo P. Okay, so F to the P 0 is divisible by P, but not divisible by P squared. This is the condition for the minimality of the convergence series. Okay, so here is kind of the general result for the minimality of the convergence series. Suppose we have convergence series of this form. F is G plus P times H. Actually, this comes from the periodic virus preparation theorem. And then for simplicity, we have the norm 1, and F is minimal on GP if the following conditions are satisfied. The first is the polynomial part is transitive, polynomial modulo P over the degree. In this case, is the same as the virus thrust degree of F. Okay, this function, polynomial function, has a full cycle given by z cos 0 and cos 1 up to cos p minus 1, where these elements consist the set of finite elements of p elements. And then the second condition is the product of the derivative of the polynomial g at the 0 up to p minus 1 is a unit in GP. Okay, this comes from the this is a condition corresponding to the condition in E2 here. Okay, and now the third condition comes from the condition E3, which says that this satisfies this congruous property. One we can observe is that actually this constant in here Wi is a product of the derivative of the polynomial at some point. Wi really depends on the I to the p minus 1. Okay. Here is the criterion for the more general case. From this result, actually we can derive the kind of the several corollary. First corollary one says that the F is the dynamic system chi is minimal on the GP if and only if the pi to the p plus 1 is minimal on the maximal ideal of GP. P times GP. So here is the minimal criterion for the pi to the p plus 1 in terms of its coefficients. When you see here, these conditions involves with the first three conditions. The first constant term and the second the term of degree 1 and 2. Okay, this congruence for the minimality is quite simple because these two systems are conjugate to each other by the transformation eta is G mod P. Okay. So there is another corollary. F is a conversion series satisfying the following the conditions. These are quite natural. Then F is minimal on GP. Using our criterion, actually, we can establish this result very easily. But this result is kind of the view as the generalization of the minimal condition for the polynomials with the GP coefficients. This result was proved by the Javahari and Rusak, whose proof really depends on the power sum involving the Bernoulli numbers. Okay, so from the congruence, actually we have to use the kind of the congruence property for the power sum in terms of the Bernoulli numbers. Okay, now I'm gonna get started with the kind of main part of my talk. Okay, so first I'm going to talk about the rational maps with good reduction. So any rational map pi on the correct line of QP of degree at least 2 expressed as a quotient of two polynomial f and g with the GP coefficients such that two polynomial has no common zeros, and also at least one of the coefficients f or g is unique. In this sense, we just say that the rational map pi is written in a normalized form. Okay, so here is the definition for the good reduction of the rational map. Rational map pi is a good reduction if its reduced function has the same degree of the given rational function pi, because usually the reduced function, degree of reduced function is a decrease by taking a reduction coefficients modulo prime p. Okay, so this function, rational function pi bar, is defined as the ratio of the its reduction of the numerator and the denominator polynomials. Okay, so usually the reduction of the polynomial with the GP coefficient is just taking the its coefficients by the modulo p. And then in the literature, there is a quite good, property for the one-list conditions. Well, one-list continuous. Okay, so if pi is rational map with a good reduction on the correct line, then it turns out to be that this rational function is one-list condition. I'm sorry, one-list continuous. In other words, pi satisfies this inequality here. Okay, so as long as we have a good rational function with a good reduction, then we have a nice, one-list continuous function. Okay, so here is I'm going to talk about the minimal criterion for the rational maps with the good reduction. These results due to the Fan Liao one. Liao is the first speaker of the today's session. Okay, so if we have a rational map has a good reduction, then its reduced function pi bar induces a map on the first line of finite field. Okay, so here is the criterion for the rational map, minimality of rational maps with the good reduction. Okay, the dynamic system first line of QP pi is minimal if and only if the following conditions are satisfied. Reduced function is transitive, in other words, minimal on the first line of the finite field. Okay, and then the derivative pi to the p plus 1 is congruent to 1 modulo p, and also if the value of the p plus 1 to the iterate, at 0 is 1 over p. Okay, so these two 1 and 2 conditions from the corresponding to the minimality of the reduced function at the level 2. And then additionally, for the case p equals 2 or 3, then we have to it's the following the inequality. I mean, the absolute value it should be satisfied to guarantee that this reduced function is minimal at the level 3. Okay, mu is 3. Okay, okay. And then we can come up with the kind of equivalent minimal criterion that is to the equivalent to the previous result, Fan et al.'s result. Okay, so my result is almost same, but we gave the alternative proof of this their result. But in the case p equal 2 or 3, actually we come up with another criterion. Basically, the first the congruence was observed by the Fan et al. In their paper, but actually we, in the case p equals 3, we have the present kind of the similar congruence for the corresponding to the p equal to 2 case. Okay, here is the things. So when you look at condition 3, so this condition replaced by the simpler condition involving the second first and second derivative of f to the p plus 1 at 0. Okay. Now I'm going to sketch a proof of main result for sufficiency. Actually, we note that condition 1 implies that the pi to the p plus 1 is one function on the maximal ideal of GP. Okay. So because of this fact, actually, we have to, it's sufficient to show that the dynamic system pi to the p plus 1 on the PGP is minimal because this condition implies that the minimality of the pi on the projected line of QP. Equivalency saying that, so this, I mean, condition is equivalent to that the chi is minimal on GP because of the two, as you see in the earlier slide, actually these two systems are congruent, conjugate to each other. So by the corollary 1, I mentioned earlier, so we have the coefficients lambda 0, lambda 1, lambda 2, first three coefficients, and then we have the minimal condition for chi, as well as the pi to the p minus 1 in terms of its coefficients. So the blue box just corresponding the condition corresponding to the minimality of level 2, and the condition in the red box, the pink box, is just the minimality for the chi at the level 3. Okay, so for the other direction, for necessity, actually it follows from the following the effects of the Fan et al. Actually, I already mentioned this theorem. So pi is a rational function with a good reduction. Then the pi is minimal on the projected line over QP if and only if its reduced function is minimal at the smallest level u, in this case the 3 for p equal to 2 or 3, and 2 mu is 2 for the more general case. So because of the this equivalent statement, especially by condition the statement 2, the minimality of pi 1 on the script beta 1 implies that its reduction is transitive. So this is what the condition assertion 1 says. Also, this, I mean, condition minimality guarantees that the kind of the existence of the conversion series pi to the p to the 1, pi to the p to the 1. Okay, so the minimality of the its a reduced function pi 2 at the level 2 implies the assertion 2. And then the for the case p equal 2 or 3, then we need to figure out the minimality of the pi at level 3 implies that the condition in the Pan et al.'s statement by doing some the algebra, actually for p equal 2 and 3, we can show that this condition is shown to be equivalent. The condition in the assertion 3 on both cases. Okay, so now I can come up with a kind of a complete minimal condition of rational maps with a good reduction for the case p equals 3. I'm sorry, p equal 2 or 3 in terms of its coefficients. For setup, so we are interested in the rational map of degree 2 of the form. I mean the A of Z over B of Z, satisfying the pi over 0 is infinity and pi over infinity is 1. I mean this rational map stands 0, 1 to the infinity, 1 to the goes to the 1. Okay, we can make like this way because we just use the linear fractional transformation G. Then I mean we can make a rational map like this in the here. So and now we want to set some quantities associated with the rational map: a pi, b pi, a pi 1, a pi 2, a pi 3. Okay, and now here is the result given obtained by the Pan et al. If pi is the good reduction in minimal on the product line of Q2, then the 8 conditions should be satisfied here. So among them, kind of the tricky computation is involved here. C8 because we have the product of the 5 odd numbers, product of 5 odd numbers here. And then conversely, this condition implies that pi is one is condition, continuous and minimal on the product line. Okay, so here is the equivalent minimal condition for this case. Okay, I mean our result, I mean the condition for the minimality is just almost same, but the condition C8 replaced by the more simpler, I mean condition C8 prime here. In this case, we don't have a kind of the product of 5 other elements in G2. Okay, so conversely, the condition C1 up to C7 and C8 prime implies that pi is one its continuous function, and also it is minimal on the product line of Qt, Q2. So after I prove this criterion, I observed that so 2 conditions C8 and C8 prime are equivalent to each other because for 5 other elements x1 up to x5, we have the congruence. The product of the xi is congruent to the sum of the xi modulo 4, and also we have to use another relation between the coefficients a pi 1 and a pi 2 plus a pi 3, something like that. Okay, so here is kind of the I'm going to give you a sketch proof of the case equal to. So using the minimal condition for the rational map with a good reduction over Q2. Okay, so the crucial thing is that we have to find the coefficients lambda 0, first 3 coefficients lambda 0, lambda 1, lambda 2 of the convergence series pi to the 3 by decomposing the pi to the 3 into a composition of a simpler convergence series of the form phi1, phi2, phi3. Okay, phi1, phi2, phi3 is defined this way in terms of the row involution and in terms of the translation by A, namely T sub A. So what can we observe that actually the phi1 and phi2 has no constant term. Okay, phi3 has only the constant term, but we have to figure out some relation involving the Tij, and then from this the minimality condition for the minimality, we can come up with the conditions for the minimality. Okay. Okay, now I'm gonna give you some example for the minimal rational polynomials in the case p equal 2. So it is known that there are no rational maps on the project line of Q2 of degree 2 or 2, 3, or 4 with a good reduction. So I'm gonna illustrate a rational map on the rational map degree 5. Here is the example of a rational map of degree 5. Its reduction modulo 2 has the degree 5 by factoring out, and then pi should be pi has a good reduction. By checking the minimal conditions, then they are satisfied. So this rational map has the full the periodic orbit of a full length. I mean, this is 12. Okay, so I'm sorry. Okay. Okay, now let's turn to the case p equals 3. As we done the case p equal 2, actually we take the rational map such that the pi of 0 is infinity, pi of infinity is 1, and then we set some quantity associated with the pi, and then we decompose the pi to the first into the composition of the 4 simpler convergence series of to psi 1 up to psi 4 using the inversion, and the translation by 1 or minus 1 or plus minus pi over 1. Okay, so you can figure out these coefficients explicitly in terms of the coefficients a and polynomial a and b. Okay, so now the result for the minimality follows from the computing the relations for the minimality in terms of lambda 0 up to lambda 2. Okay, so and then you can this relation can be expressed in terms of the coefficients of the 2 psi I. I mean Sij. Okay, and then here is the minimal condition. So it says that pi is a good reduction, and then pi should satisfy the condition A, which corresponding to the reduction map is transitive on the projective line of the F3. Here is a more important condition on the U0 and the this vector S1, S2, S3, S4. This is a product of these elements should be 1 modulo 3. So that's why we have 8 cases, and then the condition for these the congruence is kind of of the simple to figure it out. So you see here the some combination of the S12 and S22, S32, S42. This is a kind of the coefficient of the degree 2 in the 4 convergence series P1 up to P4. So, and then, so if this condition also guarantees that the pi is minimal on the projective line. Okay, here is a kind of the example of the minimal rational function. Or you have the degree 3 polynomial, 5 form polynomial, and then this function is just has same degree. So this function is a good reduction. Then by checking all datas conditions, then we say that we just see that the period orbit of the minimal rational map at the level 3 is given by this sequence. Okay. Okay, time's running over, so I have to go to the next. I mean, the main result is that suppose we have the rational map for more general case, and then it has a good reduction. The dynamic system is just the minimal on the whole space. Then if the following condition is satisfied, the first condition is that says that the reduction is transitive on the projective line of finite field. And then the full cycle is given by 0 infinity cosine 1 is 1, and then up to the cosine p minus 1. So as in the periodic polynomial convergent series, so cosine 1 up to cosine p minus 1 consists the non-zero element of the finite field. Okay, then condition 2 says that the product of the derivative of this rational map is congruent to 1 modulo p. Okay, so the third condition is looks like the similar in the convergent series. I mean, this congruence should be satisfied. This congruence here involves a certain quantity product of the derivative of the this rational function. Conversely, if these conditions are satisfied, then pi is a one-is continuous function and also minimal on projective line of QP. The idea is almost same. So we decompose pi to the p minus 1 into the p plus 1 convergent series. So you see that these coefficients of the convergent series in the red. So we compose these functions. We can come up with the terms of degree 0 and degree 1, so that the pi to the p minus 1 is equal to pi to the p minus 1 of 0, and then condition the coefficient of the degree constant coefficient. I'm sorry, the coefficient of degree, the term of degree 1 gives you condition 2. On the other hand, the condition 3 follows from the pi to the p minus 1 of 0 by using the iterating the functions. And then here is we have the rational minimal polynomial of degree 5 over Q7. So each reduction has the same degree. So pi has a good reduction. The cycle, full cycle of the reduced function is given by this orbit, and then we check out the all inherent datas, and then lambda 0 is divisible by the by 7, but not 7 squared. So that's why this system is minimal. Okay, so periodic orbit of the minimal length 56 of an induced system at the level 2 is given by this sequence. Okay, and then finally, I just point out some remarks that which the first, without changing coordinates, we can obtain that kind of the crucial relation, the derivative of the 0 at infinity, the point infinity. So this is given by the formula. It's coefficient of the A and B, the coefficient of A and B. And then, so what I observe is that from my result is that it is an interesting problem to characterize the minimal rational functions with the coefficient in finite field, satisfying the f of 0 is infinity, f of infinity is 1 in terms of its coefficient, as done as in the permutation polynomial of the finite fields, because characterizing permutation polynomials of finite fields is a challenging problem. Also, it has a lot of application to the coding theory and so on. So that's all I want to say here. Thank you.
Thank you. Let's thank the speaker. All right, thank you for a wonderful talk. Any questions from the audience?
I have a question.
Okay.
So in those diagrams where you drew one number after another, what
Yes.
does tildes mean again?
Okay, this when you have to understand the reduced functions for the product line. Okay, let me go back to that slide. Okay. Okay, where is? I'm sorry. Okay. Here. Okay, so you see here, the product of QP consists of the p plus 1 p to the n disjoint ball. It's exactly the same as like the p mod p to the, okay, a plus p to the n gp, okay, should be a partition of the p into the gp, right?
Sure.
Okay.
Sure.
Okay, as a trick for each end, there is a one-to-one correspondence between these set of these balls, okay, and the set of the vertices of a tree at the level. Okay, so kind of the number in the orbit is just representative of the ball.
Okay, thank you.
Okay, okay.
Other questions for the speaker? All right, well, if not, let's thank the speaker again.
Okay, thank you so much.
Thank you, and thank you everybody for tuning in today. Tomorrow we have another busy day, but this was a nice end to the number theory and dynamical systems.
Okay, thank you, Chris. Just let me say that tomorrow at 8 a.m. Central Time, US Central Time, we have the first session of random processes. So see you tomorrow, guys.
Okay, see you tomorrow.
Thank you, everybody. See y'all tomorrow.
Bye-bye.
See you. Bye.
Stop recording.